Thanks. Yeah, thanks for still being here. It's always tough to give a talk in the last session, but still quite an audience. That's great. So this talk is about some network design problems and how to solve them in a special type of graph, which are these low highway dimension graphs. And I'd like to start you off with an intuition of what these low highway dimension graphs are. So here you can see a map of southern Ontario. So this is where I lived just a few months ago at this point A here in Kitchener. And let's say now from where I lived, I wanted to travel to maybe Toronto on this side, or maybe London on this side, or any other points in this blue area. Okay, then the shortest path from there will always go through one of these green crosses that are called the hubs. Okay, and the idea is that, well, the shortest path will always go through the highway, hence the name of the highway dimension. And the highways are sort of sparse, and that's why there are only a few of these hubs that hit every shortest path from this point A to any of the points in this blue area. Okay, but the same is true if I take a different scale of the map. So if I zoom in, okay, so here, again, this is where I lived on King Street here. And let's say I wanted to travel to the University of Waterloo or any other point here. Again, there is a sparse set of hubs that are passed through if I take the shortest path. Okay, and I'll give you a formal definition in a minute, but before that, let me tell you what you can do with this highway dimension. So it was introduced by Abraham et al. And what they did is they explained the good behavior of certain shortest path heuristics, which were known to behave very good in practice. And what they showed is that if you assume that your transportation network has low highway dimension, then you can actually also formally prove that the running time is much better than what the worst case analysis would suggest. Okay, but what we were interested in is kind of a different approach or a different point of view, because so we were interested in NP-hard problems that typically arise on transportation networks. So for example, if you take a Travelling Salesman problem, well, you all know the definition, or also a facility location problem. And we then assume that the input is a low highway dimension graph, and now we want to solve this problem. And yeah, we have sort of a general approach to do this, but before I go into that, let me just give you the formal definition of the highway dimension. So this is a bit tricky, actually, because there are actually several definitions, so there are 3 of them. And each one is sort of a special case of the next one. And the results we obtained is using the definition 2 here, the one that's sort of in the middle, so not the most general one, but also not the most special one. And, well, I will not, to sort of avoid technicality, I will actually not give you the actual definition that we use in the end, but instead I will give you the third, the most general definition. And this is because, I mean, most properties that we actually need already follow from this most general definition. And in the end, I will also say something about why we need this more special definition here, okay? And, okay, so the third definition, the most general one, turns out to be equivalent to saying that there are so-called locally sparse shortest path covers. Okay, what does that mean? So fix a scale R, okay? And now consider the following set system that contains all the paths that have 2 properties. So first of all, it's the shortest path for some vertex pair. And the length of this shortest path is in this interval R to 2R. Okay, so here I put just some examples. Maybe these blue guys here are in this set, but of course there are many more of them. Okay, and now what I want is a hitting set for this set system. And these are going to be my hubs. Okay, so now I have these green guys here, and every shortest path of length in this interval goes through one of my hubs. That's the property I wanted, right? And the other property, though, that I want is that these hubs are locally sparse. So in particular, if you look at any ball of radius 2r, then the number of hubs in that ball should be bounded by some number that I call h. And then I call this shortest path cover locally h sparse. OK, and now it turns out that if the high dimension of the graph is h, then there is a locally h shortest path cover for any scale in the graph. OK, and even though it's actually NP hard to compute these shortest path covers, we can compute OH log h, so locally h log h sparse shortest path covers. OK, any questions to the definition? So this is probably the most technical slide I have. So
this is highway dimension h implies that, or is the implication also the other way around?
No, it's only in this direction. I mean, OK, so for this definition 3, it's equivalent. OK, but highway dimension, again, there are several definitions. And of course, any of these definitions will imply this, right? OK, so now, so now we have a graph of low highway dimension, and we want to come up with algorithms for these problems. So how do we do it? We use embeddings. OK, so what is an embedding? So given your input graph G, the embedding is another graph H on the same vertex set with two properties. So first of all, it somehow distorts the distances. So it can have a different edge set. OK, but the distance in the graph H between any two vertices is, well, close to the distance in G. And it deviates by at most some factor of delta. And delta is called the stretch or the distortion of this embedding. But what I gain is that this graph is somehow structurally simple. And in our case, we focus on bounded tree width. Okay, so we want that our embedding has bounded tree width. And of course, you all know what happens next because, well, there's tons of algorithms out there for bounded tree width graphs. So we can solve these problems then on the embedding instead of the graph. And basically, the approximation factor that you incur is given by this stretch. OK, so here's our main result then. So if we are given a graph of highway dimension h, and it has aspect ratio alpha, OK, so the aspect ratio is the ratio between the maximum distance in the graph between any two vertices and the minimum distance of any two vertices. OK, and now we get a probabilistic embedding that has expected distortion 1+ε, so you can make it arbitrarily small. And the true width is somehow bounded by all these parameters. Okay, so in particular, if the highway dimension is constant, we get a true width that's polylogarithmic in the aspect ratio. And now, well, then there are some known techniques involving these algorithms for bounded tree width, from which we can then get quasi-polynomial time approximation schemes for these problems such as TSP, facility location, and so on. Now, if you don't know what a Q-pitas is, so it works like a pita, so you get a 1+ε approximation. Okay, but the running time is not polynomial, but instead is quasi-polynomial, so n to the polylog n. And yeah, so what's interesting about this result is that, well, in general, all these problems are APX hard, which means that there are probably no Q-pitases in general. But here we show that, well, for these instances, we can do something better. Now, one comment at this stage here is that you might be worried that, OK, the aspect ratio here might be exponential, right? We have weights on the edges. And which would mean that the tree width is somehow polynomial, which of course is completely useless because the true width is always at most n anyway. But the point is that these known techniques involve a sparsification step. So if you are aiming for a 1+ε approximation, you can always assume that the aspect ratio is n over epsilon, okay? And then you get a true width that's polylogarithmic. And that's why we get quasi-polynomial time running times also, because in the end, the running time is something like n to the tree width or something like that, okay? Good, so that was a quick introduction of what we do. So let me go on with the construction of the actual embedding. I also want to talk a bit about the properties, some properties that we need to make it work, and I'll give some conclusions in the end. Okay, so what's actually going on? So let's say I fix the scale R, and now I look at the shortest path cover for the scale. And now I'm not interested in the actual underlying graph anymore, so I forget about the edges and just look at the metric. Okay? So here's that metric, and I mark the hubs. And so what happens is that there are two types of vertices. So there's a set of vertices that are close to some hub. Okay, so I call all these vertices the sprawl. And then all the vertices that are far from a hub, so in particular, so by far I mean more than distance 2r. So these are clustered into what I call towns. Okay, and these clusters have the property that, so each town has diameter at most r, and they have a minimum distance of r to everything else, so to other towns, but also to vertices in the sprawl. Okay, and good. So now what I want to do is I want to find a sort of hierarchy of shortest path covers, so of exponentially growing scales. So for every integer I will fix the scale r 2 to the I. And what I want, so now let's look at the next lower level. Sorry, there's a question.
Could you explain again what the sprawl and the towns were?
Okay, so the formal definition is a bit more complicated than I give here. So I'm just doing it a bit hand-wavy. But basically what it means is that in the sprawl, every vertex is close to some hub, so at distance at most 2r. And then, to some, so for every vertex in the sprawl, there exists some hub, right, it's close to. And the towns have vertices that are somehow far away from hubs, from any hub, right? And these are then clustered in this way. Okay, more questions? No, that's the point. We prove that all the vertices that are far from any hub are actually clustered in this way, okay? So, I mean, this is the structure of a low highway dimension graph. Because, I mean, if there were like all kinds of vertices here, then basically the intuition is you need a hub to connect through between them, right? So they would be close to a hub. That's basically the idea. Okay, good. So I want to look at this hierarchy of these shortest path covers, and so let's look at two levels here. So level I and level I minus 1, and of course for level I minus 1, I get a different set of hubs, and again a sprawl and some towns for that particular level. And now what I want to do is I want to recursively decompose the sprawl. Okay, so I forget about what's going on in these towns here on the next lower level, and instead I decompose the sprawl by taking these towns on the next lower level, and then again decompose the sprawl on that level, and so on and so on. And now if I just declare the whole graph to be one town on the highest level, okay, then what I get is what I call the towns decomposition. So now if I take any town, this town is decomposed into towns of smaller and smaller levels, okay? And I call these towns inside this town I that I'm looking at, this town on level I that I'm looking at, I call these the subtowns. And to compute my embedding, I do this recursively. Okay, so I assume that somehow I've already been able to compute some sort of embedding for each subtown. And now the idea is to connect all these embeddings together to obtain an embedding for this town that I'm looking at here. And the way to do this is I look at a well-chosen set of hubs that I won't define them formally, but it's a subset of the hubs. I call them the core hubs, and they're hubs on various levels, like in this picture here, okay? And they have some nice properties. So for one thing, it's a subset of the hubs, but still, I can show that any shortest path that goes through two subtowns will actually pass through one of the core hubs. So I didn't remove too many hubs, basically. And the reason for this is that I have this minimum distance between towns somehow. Okay, that's the idea. And but okay, they have some additional nice property, which is that actually the core hubs have small doubling dimension. So let me define the doubling dimension. So so the doubling dimension is defined for any metric. Okay, and so for this metric, let's say you take an arbitrary ball of radius 2r for any r and around any vertex. Now, if the doubling dimension is d, you're always able to find a small number of balls of half the radius, so at most 2 to the d balls of half the radius, that cover all of the vertices inside the bigger ball. Okay, and the doubling dimension is something that was introduced to sort of give a more abstract definition, or it captures some nice properties of Euclidean and Manhattan metrics. Okay, and it was studied before exactly in this setting, and in particular, what Talwar showed is that you can actually get a probabilistic embedding for low doubling dimension graphs, or metrics, sorry. Okay, so this is exactly the same theorem basically you saw before, only for doubling dimension instead of highway dimension, and the treewidth bound is a bit different from before. Okay, and now what we do is we take the core hubs, which we prove have low doubling dimension, and then we compute one of these embeddings given by Talwar's result on the core hubs. And now what I want to do is I want to connect the embeddings of the subtowns through the embedding of the core hubs. Okay, that's sort of the rough idea. And to give you an intuition of why this works, why you get a low treewidth embedding, let me just give a very rough overview of what we do a bit more concretely. So we start with this embedding given by Talwar on the core hubs. Because it has a low tree width, it comes with a tree decomposition. And okay, just by induction, the same is true for every subtown. I have an embedding there that I pre-computed, comes with some sort of tree decomposition. And now what I do is for every subtown, I will look for the closest core hub and look for the bag in this decomposition that it's in. And now I stitch together these tree decompositions. Okay, so I just connect this tree decomposition of the subtown to the bag that contains the closest core hub. And now I add some edges. So in particular, what I will do is I will add an edge between every core hub in this particular bag that I identified with every vertex of the subtown. Okay, and well, in reality, of course, these edges go between the embedding and these embeddings and this embedding of the core hubs. And then I have to prove that somehow the expected distortion is 1+ε, which is, it requires a proof, not trivial at all, but can be done. And the other thing is what I also need to do is, just because I stitch together this tree decomposition, is not going to give me a valid tree decomposition. So I have to somehow shift around some vertices in my bags and prove that my bags don't grow by too much in this process. And again, also this can be done, and the treewidth bound that I get is this. Okay. So just a very rough overview of what we're doing. Good. So yeah, let me talk a bit about some properties, in particular, like how we show that the core hubs have low doubling dimension. Okay. So you might have noticed that the definitions of the highway dimension and the doubling dimension have some similarities. So both involve some sort of ball of radius 2r with a bounded number of objects associated with it. So in one case, it's the hubs inside the ball. In the other case, it's the balls of half the radius that cover every vertex inside this bigger ball. So to prove that the core hubs have low doubling dimension, what we do is we look at an arbitrary ball of radius 2r. Okay, we identify the level of this ball and look at the hubs, the core hubs of that particular level, so the green hubs in this picture here. And the idea is, well, I know that somehow there's only a few of these hubs inside this bigger ball. So if I just take balls of half the radius around those, I'm hoping that I will cover all the core hubs inside of this bigger ball. Now, there are several issues that arise with this approach. So this doesn't work like I describe it here. I only want to mention one problem, which is the following. Well, it might happen that you have to actually take balls of half the radius around hubs outside the big ball to cover core hubs inside the big ball. Now, that's a problem because we don't have a bound on these core hubs outside here. And this is where the definition 2 comes into play. So this more special definition. And what we can show is that actually, if we use this more strict definition, we can also bound the hubs that are in the vicinity of a big ball. Okay, so in particular, there's at most h square hubs somehow outside here that are close to this big ball. So we can actually use them as centers for balls of half the radius. Okay, so yeah, just some conclusions. So of course, we are not the first ones to think about like special graph classes that somehow capture transportation networks maybe better than just a general graph and trying to solve these problems. In particular, I mean, these algorithms like for planar graphs or Euclidean metrics are pretty famous. But I want to make the case that these low highway dimension graphs somehow capture some transportation networks that are not captured by these cases here. So in particular, let's look at air traffic networks. Okay, so this is a transportation network, and usually an air traffic network is a so-called hub and spoke network, which means that the smaller airports all connect to big airports from which you're able to reach faraway destinations. Okay, and of course you can see from this picture alone that these graphs are not planar. Okay, that's pretty obvious. But also, I mean, because all these small airports here connect to these big airports, you get high-degree stars in your graph. So the doubling dimension will also be fairly large. Okay, but you can, if you just put a hub onto each of these big airports are pretty sparse, so you can argue that that the highway dimension will actually be pretty small for these graphs. Okay, and so what this also shows is that so we heavily rely on this result for low doubling dimension metrics by Talwar. And I mean, he generalized this result basically for the Euclidean metrics. And so it's sort of this geometric setting. And what we do is we extend these tools for the geometric setting onto something broader, which are these low doubling dimension metrics. And OK, just in the very end, just to mention some open problems. So actually, OK, so we get these quasi-polynomial time approximation schemes. But what we actually don't know is whether the problems are actually NP-hard on these graphs. Okay, and well, one obvious question also, even if they are NP-hard, it's not clear how to get pitas. Okay, and of course, one additional interesting question is whether we have to rely on this more special definition 2, or if we can actually do it with this more general definition from which we actually get most of the properties that we need in the end. Right? And yeah, so that's it. So thanks for your attention.
So thank you for your nice talk. Other questions?
So do you know that the dependence on alpha, so let's say the highway dimension is constant, so then you're getting polynomial and the log alpha.
Yes, yes.
Do you know examples where you need to do something?
Where I need to lose something? Well, OK, let's say it this way. I mean, even a complete graph can have highway dimension 1. Right? So so it's not minor closed. In particular, a low highway dimension graph does not have small tree width. So the tree width of a low highway dimension graph can be n, can be arbitrarily large. So yeah, I have to. There are examples where yeah.
Do tree metrics have bounded highway dimension?
So even a tree can have arbitrarily large highway dimension. So very simple example is just a star. I mean, if you take, yikes. So if you take a star and just add, like subdivide the edges basically, then if you take a ball that contains everything, then these guys might be shortest paths. Okay, so you have to hit every one of these edges, so you have to put a hub on everywhere here, so it can be arbitrarily large.
How far are your generalization from the spaces with bounded doubling dimension?
Sorry, say again.
How far are your spaces from the spaces with bounded doubling dimension?
Okay. Yeah. Well, I mean, again, so a star has highway dimension 1. Okay, because I can just every shortest path goes through the center vertex, but the doubling dimension is arbitrarily large for a star. No, also not. So if you take a grid, then the grid has a small doubling dimension. Okay, but it has a square root n highway dimension. Okay, because so if you take a grid, okay, and now you take like a ball somewhere inside here. Basically, you have to hit every one of these paths that like go through here, right? So you get something like square root n.